Okay, so we're going to continue with 2.7. At the end of the last video, I left you with two functions, f and g, as follows. And our task was first to find their domains. So let's go ahead and find their domains. Well, the domain of f is essentially defined by the denominator not being 0, and for g of x, it's the domain, is defined by a similar procedure. It's that, well, it's twofold. One is that square root of x plus 1, that can't be 0, and whatever's inside the square root, which is x plus 1, must be at least 0. So what I'm doing is I'm writing the defining conditions for these two domains. So if we solve x squared minus 4 equals 0, that means x squared is 4, or x is plus or minus 2. So our domain of f is everything except those values. So the domain of f in shorthand notation is simply x, where x is not these two numbers. In interval notation, that means we have everything below -2, as well as everything between -2 and 2, as well as everything beyond 2. So that's the domain of f. For the domain of g, if you combine these two conditions, well, this thing being 0, that's the same as x plus 1 not being 0, right? So if you combine this with x plus 1 greater than or equal to 0, you get the single inequality x plus 1 must be strictly greater than 0. That's the defining condition to be in the domain of g. So this means x has to be bigger than -1. So the domain of g is the open interval -1 to positive infinity. So recall that when we're going to combine these functions additively or multiplicatively, we need to first, we're going to end up needing the domain of, we're going to end up needing the intersection of these two sets. So let's call this set A, let's call this set B, and let's first compute what's in common. So again, sometimes it's easier to think of this as the defining condition. So I need x to not be plus or minus 2, and I need x to be greater than -1. Well, so here's negative. So if I put it on a number line, I can't have -2. Here's a -1. I need everything to be larger than -1. But I also have to remove 2. So if you combine all of this, what do you get? You get -1 to 2, as well as 2 and beyond. All right, so if you need both of these, both this to be true, that x is not -2 and x is not positive 2, as well as x being strictly greater than -1, that's the intersection, that's what's in common. So if we write, for example, f of x plus g of x, which is the function f plus g over all of x, what is that? Well, that's 1 over x squared minus 4 plus x over square root of x plus 1. Or if we write, let me just reverse the order here, just to keep it consistent. This is f plus g of x, which is f of x plus g of x. F minus g as a function of x, that's f of x minus g of x. That's 1 over x squared minus 4 minus x over root x plus 1. And then there's f times g of x, which is f of x multiplied by g of x. And that is the quantity 1 over x squared minus 4 times the quantity x over root x plus 1. What is that? That's in the numerator x times 1. And the denominator is x squared minus 4 quantity times the square root of x plus 1. And the domain of all of these three, let's give these names 1, 2, and 3. The domain of these, the domain for 1, 2, and 3 is exactly the intersection of the domains of f and g, which we just saw above was negative 1 to 2 as well as 2 to infinity. Okay. Now, the last part here is the domain of f divided by g. Well, remember, this is exactly still A intersection B, but we also need g of x to not be 0. That's the only additional condition. So the question is, when is x over root x plus 1 equal to 0? Well, if you want to do it systematically, I guess you can cross multiply by x plus 1, square root of x plus 1 on both sides, and what you land is just x itself must be 0. So what we can't allow x to be 0. So in particular, x can't be 0. So we need this condition to be true as well as us to be in the set A intersection B. This and this intersection, the set negative 1 to 2, 2 to infinity. So essentially 0 sits right here, right? Inside of between negative 1 and 2. So we have to delete that point. Let me just do a visualization of this on the real line so you see what I mean. So we're right now including the whole piece from negative 1 to 2, but then at 0 here, we have to make a little opening there. We can't allow for 0 to be part of our domain anymore. So we eliminate that point. Excuse me. And then we get everything beyond 2. That part's okay. So what we finally get is, so the domain of f over g, which I haven't done algebraically yet, I'll do that in a moment, that's negative 1 to 0, union 0 to 2, union 2 to positive infinity. Okay, so as you can see, finding the domain of a combination of functions, it's a bit more intricate than finding just a domain of a single function. Last but not least here, let me write down what this actually is algebraically. This is 1 over x squared minus 4 divided by x over root x plus 1. This is 1 over x squared minus 4 times root x plus 1 divided by x. So we have on the numerator square root of x plus 1, and the denominator we have x times x squared minus 4. So if you multiply everything out, you get x cubed minus 4x. So this is the algebraic version of f over g. Okay, so this was the exercise from last time. What we're going to do now is we're going to define a new way of combining functions, which is called the composition of functions. To compose functions. And what we're going to label this is we're going to have, so to compose a function, we're going to say f composed with g. And notice this little open circle in the middle. That's the symbol for composition. This is simply f of g of x. It looks pretty straightforward, but there's a fair amount that is going on, and it leads naturally to some more interesting concepts like inverse functions. But before we get into all that, let's just compose. So let's just do an example directly. Let's let f of x be x squared minus 2, and g of x be x plus 5. And let's just compute f composed with g of x. Okay. And maybe let's do g composed with f of x as well. Okay, so let's start with f composed with g. Well, f composed with g of x, that's f of g of x. Now, what does that mean? That means wherever I see the x here, so for example, so let me just write this down here after the side. F of x, again, is x squared minus 2. So effectively, g of x, this is going to replace any x in the function f of x, right? So here, where are the x's? Well, here are the x's right here. So f of g of x is g of x quantity squared minus 2. Because I'm substituting wherever there's an x in the function f of x, I'm replacing that, whoops, sorry, I made a typo here, not with the function f of x. Well, replace any x in the function, I guess I didn't complete the sentence, sorry. Replace any x in the function f of x with g of x. So instead of there being an x here originally, right here, there's now g of x. Okay. Well, what was g of x? Just rewrite that. That was x plus 5. So this is now x plus 5 squared minus 2. So this is x squared plus 10x plus 25 minus 2. And again, here I'm using that algebraic formula, that a plus b squared. This is a squared plus 2ab plus b squared. So this is the a squared, this is 2ab, this is b squared. Combine everything, you get x squared plus 10x plus 23. Okay, so this is the function f composed with g of x. Let's do the other way, or let me actually leave that as an exercise. So exercise, and we'll do more with composition next time. So find g composed with f of x. So let's do one more part here. And let's go ahead and have it, so evaluate f composed with g of, say, 2 and g composed with f of 2. Okay, where again, f of x, let me just put it in the box here, f of x was x squared minus 2, g of x was x plus 5. Okay, let's stop here for now. We'll do more in the next round.